Okay, we are live. Hello, everyone, and welcome to this Latin American series of webinars. So today we have Basabendu Barman talking about dissecting the dark sector with the gravity. And so we are super happy to have you here, Basabendu. So Basabendu finished his PhD at ITC Guwahati, and then he had a couple of postdoc appointments, one in this supergroup in Colombia, in the Universidad de Nariño. And then he moved to Warsaw. And very recently, I think a couple of days ago, maybe last week, he joined the SRM University in India, right? So now he's a young professor there. So thank you very much, Basi, for accepting this invitation. So please, you can go ahead.
Good, great. So let me first share the screen. Please try to. Can you see my screen?
Yes, perfectly.
Okay. So yes, of course. First of all, many thanks to the organizers for giving me this opportunity, for the invitation. And it's good to see all the familiar faces, all the virtually. So as Nicolas has already introduced, that I'm going to talk about something like dissecting the dark with gravity. It's like how one can study physics beyond the standard model, utilizing gravity as one of the tools. So this talk is based on a couple of papers which are shown over here, which I have worked with different collaborations over last 1 year or so. So before I really plunged into all the details of the models and calculations and show you the plots, etc., let me start with a very brief prologue, just to build the framework of whatever I'm going to talk about. So this first few slides will be very, very pedagogical, very well known to almost all of us. So this will be a lightning review of whatever we have learned so far regarding a standard model and a bit of beyond the standard model. We know that why the standard model is nearly perfect, but not absolutely perfect. And we will ask the question that what happens about dark matter, or what happens with the matter-antimatter asymmetry. So these are the motivations of going beyond the standard model. Of course, there are many more motivations. That's why I've kept the fourth point blank. But I will be talking about mostly about these two scenarios regarding a particle dark matter candidate and generation of matter-antimatter asymmetry. So let us begin. So as we know that this is a recent picture of the standard model of particle physics after the great discovery of the standard model like Higgs boson, which perhaps is the only spin zero boson that the nature offers. And this completes all of the standard model particle content. And we know that the standard model has been tested over and over in different experiments, in different experimental facilities, and it has been found to be robust. So this is a very nice model that can explain the nature to a great extent, with an unbelievable precision, of course, that I must say. However, there are still some things that the standard model cannot really do, and that's where the requirement of new physics comes in. So it still leaves some window open to go beyond the standard model and seek for new physics signal. And one of the many reasons is, of course, the explanation of the light neutrino masses. As we know that the standard model neutrinos are massless because of the very structure of the standard model itself. But on the other hand, we have oscillation experiments which have told us that neutrinos are not exactly massless, but they have a very tiny bit of mass. So in order to explain this tiny neutrino mass, one has to add more particle content with the standard model fields. And there are many ways to generate light neutrino masses, as we know. So this is one of the reasons that people seek for beyond the standard model signature. Another reason being the matter-antimatter asymmetry. Again, here comes experiments which have told us that there is more matter than antimatter in the universe, and that's how the universe created. We do not know exactly when this happened, but we do know that the standard model has all the necessary ingredients to explain this matter-antimatter asymmetry, just not in the adequate amount. So in order to explain the observed amount of matter-antimatter asymmetry, again, one needs to go beyond the standard model. And finally, this very crazy pie chart, which tells us that only 4% of the universe is visible to us. And 72% is, of course, made out of some exotic thing called dark energy, which is, of course, not my area of expertise. That's why I'm not going to go over there. I will rather concentrate on this very small, green region, which tells the 24% of matter energy budget is made up of something called the dark matter. So these three will be our guiding principle for the next couple of minutes, whatever we are going to talk about, and we will try to explain the matter-antimatter asymmetry together with dark matter, and also we'll try to address the light neutron mass generation through some mechanism with the help of gravity. I will tell you about it. But now let us try to ponder over the fact that how do we are confident about the presence of dark matter. We know that there are a plethora of experimental evidences which mainly come from gravity and astrophysics, cosmology and astrophysics. And of course, the very earlier evidences are coming from what we know as the galaxy rotation curve, which clearly shows that as we move away from the central bulge of the galaxy, which is the most luminescent part, and go towards the outskirt, we see there's a deviation from the predicted nature from theory of the rotational velocity of the stars from what we observe. And this tells us that, well, there are indeed some exotic matter which are non-luminescent, maybe non-baryonic, and these are playing the role in influencing the rotational curve or rotational velocity of the stars in the galaxy. And that's why we see this deviation from what we expect. The next very solid evidence comes from what is known as the bullet cluster, which is formed by the collision between the two galaxy clusters. And this really tells us that the dark matter is non-interacting, at least at the scale of the galaxy cluster. And if you look at the picture, that when the two galaxy clusters collide, then the baryonic matter, which is highly interacting, is basically concentrated in the middle, and that's create this shock or a wake kind of a shape, while all the masses which are contained within the dark matter are actually lying outside, which one can find by mapping the whole thing with the help of gravitational lensing. And at the fourth, the most important evidence of the matter energy budget comes from the cosmic microwave background radiation, which are nothing but the relic photons that are coming to us from the very early universe, maybe from the Big Bang. And one can measure actually that the very tiny amount of temperature anisotropy in this microwave background. And this tells us that, well, indeed, there is only the 4% of the universe is visible, and 24% of the universe is made up of this exotic candidate, which is called the dark matter. Now, from all these evidences, of course, we do not know exactly what sort of particle, if at all, dark matter is, but we are sure about some of its properties. For example, it does not couple to photon or couples to photon very feebly. That's why it's kind of dark. Of course, it talks to the gravitational forces, and that's why you see the rotational curves are deviating from our expectation. And since we can measure its relic density, so it's still around today, which makes it super stable, at least at the lifetime of the universe. Now, as a particle physicist, we always try to explain what kind of particle nature the dark matter can be, and we go back to what model we have already at hand, which is the standard model. And we try to see that if any particle within the standard model can be a good dark matter candidate. And in order to do that, that candidate has to satisfy these three properties that I have listed below. And we see that, well, the standard model neutrinos exactly have all those properties. They're basically light, they only have weak interaction, and they're stable. However, these particles are so light, they cannot make up all of the dark matter abundance that we see today. And there is a even more important drawback of having all the dark matter as neutrinos, which is the structure condition, because neutrinos are typically known as a hot dark matter candidate. So they have a very large free streaming length, which means that they erase all the small scale structures. So the large scale structures in the universe start forming earlier, and then the small scale structure form later. And this is against our observation, typically from the n-body simulation. We know that all the small scale structures form first, and then they coalesce through gravitational interaction, and the large scale structures form. So in order to have the right structure formation and also the adequate amount of dark matter relic density, again, one needs to have some cold dark matter candidate. Therefore, one has to have some candidate beyond the standard. Now, the question is that what sort of particle this dark matter can be, the beyond the standard model particle, and what can be its mass range? Well, it can be anything between, let's say, a pin and an elephant. So it can be as light as 10 to the minus 22 eV, given that it's kind of a boson. It can be as large as 10 times the solar mass if it's a primordial black hole, and anything in between these two scale can be a good dark matter candidate as long as it has those three properties intact. However, if you look at this WIMP kind of a scenario, these particles have been stealing the show for a couple of last decades because of the fact that WIMPs give the hint of new physics around the weak scale. Due to the fact that the WIMPs produce the right amount of Lake density through a weak scale cross section, and that's sometimes called the WIMP miracle. And that's made all of us excited because the weak scale is something that we always want to probe. We always search for new physics around the weak scale. However, tremendous experimental efforts have been put, in order to search for WIMPs. But typically, WIMPs people have been looking for signature of this kind of weakly interacting massive particles through what is known as direct detection experiment, where you have some experimental facility having some inert nuclear sitting on the Earth, and the WIMP from the local halo of dark matter comes and collides with it, and we measure the recoil velocity, and that recoil velocity or recoil energy that gives us the number of such events. But no significant number of such recoil events have been found so far, and that is why we do not have any evidences of WIMP kind of dark matter in the nature. Also, on the collider frontier, we do not see any sort of missing energy excess, at least in a significant level, which can give a hint of new physics around the weak scale, or typically the WIMP. So therefore, people have been looking for alternative dark matter production mechanism, and many have been proposed. One of which I will be talking about mostly is called freezing. And the difference between WIMPs and particles, these are freezing, these are called FIMPs, is the fact that if you look at this plot in the left panel, that this black curve shows how the relic abundance or the yield, or rather the number density of a WIMP kind of a particle evolves over time. So these particles are actually in equilibrium in the early universe. At some point of time, the interaction rate falls below the Hubble rate, and then it saturates. In the contrary, these FIMP kind of particles are never in equilibrium, so they are produced gradually from the visible sector through some interaction, depending on what sort of model you build. And at some point of time, they freeze in and produce the observed relic abundance. But because you have to assure that these particles never come in equilibrium, so the freeze in or the FIMP kind of particles have very, very feeble interaction with the visible sector, and that makes them very challenging to detect. Of course, not entirely impossible. But one important fact is that since these particles are produced out of equilibrium, they always carry a memory. By memory, I mean they have an information of the background cosmology or the era at which they are produced. Unlike the WIMPs, because they equilibrate at very early stage, so they lose the memory of the production mechanism. This I will explain in a moment. So now going ahead, so as I was telling you that there is one more reason to look for physics beyond the standard model, and the reason being the Baryon asymmetry. And again, the evidences comes from the tiny measurement of temperature anisotropy of CMB, or the measurement of the light element abundance around the Big Bang nuclear synthesis or BBN, and both gives you the same result, that there is more matter than the antimatter. And of course, this cannot be an initial condition for the universe to begin with, because we know that there was a time when the universe went through a phase called inflation, which of course solves other puzzles that I'm not going to talk about. But due to this first expansion, whatever the asymmetry that we produced in the very beginning, that we washed away. So it must have been produced dynamically at some point of time. And this dynamical generation of Baryon asymmetry needs to satisfy three conditions, which are known as Sakharov conditions, which tells us the underlying the model or the framework has to be baryon number violating, which is understandable because they're producing more baryon than the anti-baryon. So this charge has to be violated. It also has to be C and CB violating. This is a bit subtle, but it tells that, well, whatever the rate of the process at which you produce the baryon should not match with the rate of the process that produces anti-baryon, so that they cancel each other out. And also, whatever the process that produces this baryon asymmetry should go out of equilibrium at some point of time, because again, otherwise it will just wash out if it equilibrates with the standard model path. Now, again, if we look back at the model at our hand, which is a standard model, We know that the standard the Baryon number within the standard model is not, it's an accidental symmetry, and it is broken by the quantum correction, the triangle diagrams. So Baryon number validating processes are there, and these processes are actually very efficient at very high temperature, but they exist within the standard model. And also the weak interactions violate CP maximally, and we know that how to measure it. It's encoded in the CKM, and we have a measurement which is typically known as the Charles-Clark invariant, but it's too small. It cannot provide the observed asymmetry, of course. And thirdly, this out of equilibrium condition is actually satisfied during electroweak phase transition, formation of the bubbles, etc. But given the Higgs mass, the electroweak phase transition is not, of course, not strongly first order, but rather it's a crossover. And therefore, to have a very strong departure from equilibrium, A, or to have a new source of CP violation, B, we need to again go beyond the standard model and need to add some more ingredient with the standard model so that we can explain this dynamic generation of Baryon asymmetry. And one of the elegant ways is called leptogenesis, which produces lepton asymmetry in the leptonic sector and then shifts to the baryonic sector through some non-perturbative process, and that can generate the observed Baryon asymmetry. But the goodness of this kind of a process is that it also connects the neutrino mass with it, so you can kill two birds with one stone. You can of course explain the generation of Baryon asymmetry, but on top of that, you can also explain how the tiny neutrino masses can be generated. So with all this in our hand, let us first try to understand that why we are talking about all these things, all this like discretely connected things, but they have some underlying connection altogether. So my point here is that you have two numbers to satisfy. One is the dark matter relic abundance, which is 0.1, of course. Another number is the Baryon asymmetry at present universe, which is of the order of 10 to the minus 10. This can be done with, of course, with the help of particle physics, and particle physics needs basically the interaction, which we provide by writing down the Lagrangian, which contains the couplings and the masses and the particle content, etc. And with that, you can compute the cross section, which can give rise to adequate amount of dark matter, which we can find out by solving the Boltzmann equation that determines how the number density evolves with time or as the universe expands. And on the other hand, the same model, with the help of the same model or with the help of some more exotic model, you can of course explain the Baryon asymmetry, as I was telling you, for example, leptogenesis. So particle physics can do both the job. But on the other hand, inevitably we have gravity, because gravity, has this democratic coupling with all sorts of matter particle, which is suppressed by Planck, and that's why we cannot really ignore its presence. Of course, the standard model does not have it, but we cannot really say that, well, we can totally ignore it. So gravitational production is always there, whether we want it or not. It's always there because it has this coupling of Planck suppressed coupling, which is one cannot ignore. So gravity can produce, of course, the dark matter in adequate amount. However, it does not provide you a source of CP violation. So in order to have a CP violating process, you need to rely on particle physics. But both of these sectors are connected through cosmology, because you always produce these particles in a background in an expanding universe, which is controlled by this Hubble, the rate of expansion. So what we're trying here is to bridge a gap between particle physics and gravity with cosmology, such that we can explain these two long-standing puzzles called dark matter and Baryon asymmetry at the same time, or maybe differently, one at a time. Now, coming to the observational aspect of it, particle physics, of course, has many observational facilities. For example, the colliders. There are direct detection experiments. There are neutrino experiments, which not only search for neutrinos, but can also search for very feebly coupled exotic states, etc. But on the gravity sector, we have the gravitational wave, and thanks to LIGO, we have already detected them, and we know that the future gravitational wave experiments can be more and more sensitive in detecting even low or high frequency gravitational waves that I will try to show you. So my point here is that gravity and particle physics, together with the help of cosmology, can be a good probe or a good instrument to explore physics beyond the standard model that can explain dark matter and Baryon asymmetry together. This is I will try to show you how. So now that I have set the stage, now I will start the discussion of how to explore the dark sector with the help of gravity, and how can we observe all such models, or can at least predict or put constraint on them. So these four will be my point of discussion. First, I will start with a very simple model which utilizes a portal provided by gravity that can help in explaining dark matter and baryon asymmetry, that can also be constrained from primordial gravitational wave, typically low frequency. Then I will also discuss a typical scenario where one can have high frequency primordial gravitational wave coming from a different source. And finally, I will tell you how a non-minimal coupling with the gravity can help you to resolve these two dark matter and baryon asymmetry questions at the same time. And at the end, I will conclude. So let us begin. So let us first try to start with a very simple model. We of course have standard model, which is intact. We cannot fiddle around with that. On top of standard model, we add some singlets. By singlets, I mean singlets under the standard model gauge symmetry without disturbing the gauge symmetry at all. And these singlets can be scalars and fermions. Typically, we add one scalar and 3 right-handed neutrinos. And this one scalar will act as an inflaton, which will be responsible for the inflation of the universe. And at the end of the inflation, it will also reheat the universe. And these 3 fermions will be our dark matter and the source of CB violating asymmetry. And then, of course, once you do that, and if you expand this flat metric with a small perturbation, we will always have this dynamical field called the graviton. And you end up with this kind of a Feynman diagram where you see that all these exotic particles, of course, you can produce a standard model as well, because everything is connected through the same gravitational channel in the final state. And this can happen during by the annihilation of these phi's, which are typically the inflaton. But in initial state, one can also have the standard model as well. So what I will try to show you that once you produce these right-handed neutrinos can be stable and give rise to a good dark matter candidate. But neutrinos can also decay through this trilinear coupling, trilinear Yukawa, typically responsible for leptogenesis, and further this can produce the baryon asymmetry. So I will refer N1 as the dark matter candidate, which can or cannot be stable. I will discuss both scenarios, and with the other 2 neutrinos, we can generate the asymmetry. And I choose this phi to oscillate in a potential which is typically known as this hyperbolic potential, the attractor potential. And there is only one free parameter in the potential, which is lambda, which is not exactly free, but can be constrained from CMB observations, requiring that it produces right amount of E folds so that this can give rise to inflation. So this is my setup. So standard model with some singlet fields in terms of scalars and fermions. So now let's move on. Now, once we have that, if you remember, this k is basically the exponent of the field in the potential, which goes like phi to the k. So if you produce all the standard model particles, let's say typically the Higgs, through only gravitationally mediation of this graviton, then you need k larger than 9 such that you can reheat the universe above the BBN temperature, which means before the onset of the BBN, because you do not want to mess up the generation of the light element abundance. However, with the help of a non-minimal coupling between the Higgs and the gravity, you can actually you can constrain this number and turn it down to k larger than 4. And this k larger than 4 is interesting because it says that the generalized equation of state for this inflaton is larger than 1/3. And remember, this omega is a ratio of basically p and rho, and for radiation, p equal to 1/3 rho. So this refers to some particle which is stiffer than the radiation. So one needs a fluid or during the reheating, the background should be stiffer than the radiation such that one can reheat the universe to the adequate amount. And this non-minimal coupling is done through this usual prescription that you write down everything in the Jordan frame, then you move to the Einstein frame so that you can have all the interactions. And once here we do that, we come up with typically these 5 diagrams, which tells you that how the standard model and beyond standard model particles can be produced through minimal and non-minimal coupling. And minimal scenario is basically mediated by this S-channel mediation of graviton, while the non-minimal scenario is basically all the 4-point diagrams, which are guided by these couplings. You see, all these couplings have masses of the fermions in the top, thanks to the helicity of the fermions. So one can assume that this fermions masses has to be very high so that they can surpass this suppression from the Planck, because the size have to be smaller so that the perturbative nature of the couplings are maintained. So what we will try to do now is to produce dark matter which are N1 through all these processes, and also the next heavier neutrino N2 through these channels. But we will remember that we will only consider to non-thermal leptogenesis, so there is no contribution from standard model in producing these heavier neutrinos. And the universe will be deheated through the pair annihilation of this inflaton to the standard model path, typically to the Higgs. So before I typically show you the parameter space, etc., I will take a very small detour, because I will try to tell you the story about this primordial gravitational wave, which are stochastic in nature. And these waves, as we know, they are unlike the astrophysical sources. They are generated during the inflation from, let's say, the tensorial perturbation of the metric. And these are basically typically the quantum fluctuations. And these fluctuations start inside the Hubble. And because during inflation, this Hubble radius is basically shrinking, therefore they exit during the inflation. And at the end of inflation, when again it starts rising, these fluctuations or the modes, they start re-entering the horizon. And depending upon at what era these re-entrants happen, these modes can either be scale invariant if the re-entrance happens during radiation domination, or they can have a blue tilted part if they re-enter during this stiff epoch that I was telling you, which is required to reheat the universe accordingly. Now, this blue tilted spectrum has a problem. The problem is that it's in conflict with the delta N effective. Delta N effective is a measurement of how much of extra relativistic degrees of freedom you can allow around the BBM apart from the standard body. And we know the gravitational wave is basically the scaleless radiation once the source is switched off. So here, just I try to show you the thing that if you have a minimally coupled scenario, then all these curves are in conflict with this BBN bound, which are shown in blue, which tells you that the minimally coupled scenario is basically completely ruled out. While if you increase this non-minimal coupling and put some non-zero value, you can reduce this tension and make this scenario viable. And the reason for this boost is very, very simple, that this ratio over here tells you that my gravitational wave, the energy density gravitational wave to that of the radiation, typically proportional to the momentum at the horizon crossing, which is nothing but the Hubble at the horizon crossing. So therefore, when the horizon crossing happens during the radiation domination, so these are constant, which are shown by this straight line if you follow the red curves. But if this horizon crossing happens during the inflaton domination, during the reheating, then you see this blue tilt, which is shown by this upgoing red curve. So the point here is that I will show you in the very next slide that if we consider this minimally coupled scenario, this completely rules out a part of the parameter space. So this is basically how the parameter space looks like. In the bottom left panel, I show you the relative density allowed region in reheating versus K plane. Remember, K is the exponent for this inflaton phi, which determines the equation of state for the inflaton. Now here, if you follow each curve, then for each dark matter mass, there are two curves, because the relative density is satisfied twice, depending upon whether you are at a low reheating temperature or at a high reheating temperature. In the low reheating scenario, the phi scattering dominates. At the high reheating temperature, typically the contribution from path dominates. And here you see the dark matter has to be as massive as a PeV in order to surpass the Planck suppression due to gravity. And again, this blue line shows whatever I was telling you in the very last slide, that it is excessive gravitational wave, which is in conflict with delta N effect. On the right hand side, each curve show the right amount of Baryon asymmetry that one can produce depending on the choice of the mass of this N2. However, this green region is basically underproduced because in conflict with this kinematical suppression, as I was telling you that we are considering non-thermal leptogenesis. So all contribution comes during reheating, where a pair of phi goes to a pair of N2s. And as N2 becomes heavier, so at some point of time, it cannot be produced. Again, the excessive gravitational wave, totally rules out some part of the parameter space. due to the conflict with BBN bound. So now if I allow this dark matter to decay, let's say the dark matter decays through some channel, but the decay lifetime is large enough that it can be as large as the lifetime of the universe. So it's still a stable relic. So now if I allow this dark matter to decay, remember the only channel through which this dark matter can decay is the trilinear Yukawa LHN. So it always decays to leptonic final state, typically to neutrinos. And since this dark matter is at least a PeV scale dark matter, so all the neutrons it produces are basically super energetic. And we know that such neutrons have been seen at the ice cube experiment. And we are not trying to exactly fit the data, etc. But we are trying to say here is that there is a provision for this in this setup to have a PeV neutrino and then have a dark matter which decays through this trilinear coupling, such that they can produce these high energetic ice cube events at the experimental frontier. So this kind of a gravity-mediated scenario is not only can be tested with the gravitational wave, but can also leave their imprint at the ice cube facility or through production of the high energy neutrino events that can be found in some other experiments as well. So this is the net parameter space which I put it in the mass plane. N1 being the mass of the right-hand neutrino that plays a role for the dark matter, N2 being the next massive right-hand neutrino, the decay of which produces Baryon asymmetry. And here each of these differently colored points, they correspond to different non-minimal coupling. And this typically minimally coupled scenario is totally forbidden because of BBN bound on delta N effective. So one has to go beyond this minimally coupled scenario and typically choose a non-minimally coupled sector. And however, one cannot go beyond 10 because then the right-hand neutrino becomes so heavy it cannot be produced through the pair annihilation of a pair of inflaton to produce the right amount of Baryon asymmetry. So this is the compact nature of this framework. So the upshot of this all discussion is the fact that the discovery potential for the primordial gravitational wave not only can provide you a window to look into beyond the standard model physics, but can also give you some idea about the early universe cosmology. Typically, that whether the universe going through a period where the inflaton energy density redshifted faster than the radiation, which is typically known as the stiff epoch. So this is one reason of having a primordial gravitational wave. But typically one can do more with this primordial gravitational wave, and one can look into the coupling of inflaton with a pair of standard model particles with the help of the same primordial gravitational wave originated from inflation. And how can we do that? So let us consider that my inflaton couples to a pair of standard model particle, visible sector particle. So at the end of reheating, it decays perturbatively into a pair of standard model particles that can reheat the universe. And now if the inflaton oscillates in a steeper potential, which is not quadratic, then of course its mass is not constant, but it becomes field dependent. And then one can parameterize its decay width, typically which looks like over this. And this parameterization is valid because of the fact that my mass is no more a free parameter, but depends on the time and therefore on the scale factor as well. And here I just put this gamma phi E and beta in blue, which are completely determined once we specify what sort of decay channel we choose. So this F over here can be any particle of any spin. It can be a pair of scalar, a pair of gauge boson, or a pair of Fermi. So now with the help of this, again, we can see how the energy density of the two components, typically the inflaton and the radiation, evolves with time by solving the Boltzmann equation. And one can show that this radiation energy density or the inflaton energy density depends on two free parameters, which is this gamma phi E, basically which contains the information of the coupling, meaning the information that to which final state this inflaton couples to. And the other is this N, which determines the slope of the potential during reheating. So there are three free parameters basically in this model, which is this coupling, this N, and another one is lambda, which is the scale of inflation, which has an upper bound from the measurement of scalar to tensor ratio. And here I just show you one example plot by choosing this, by fixing some of these values. And of course, here, as one expects, that this rho phi falls faster, so such that the reheating is the onset of the point when the radiation energy density dominates over the inflaton energy density, which is shown by this red curve. And the slope of these curves will change once you choose different set of parameters, typically these n values. So now what we can do with this, we can again compute the blue tilde spectrum for the gravitational wave, but now this will depend on our free parameters, which are this scale of inflation, this gamma phi e, which contains information of the coupling, and this n, which decides that how steeper this potential can be. And therefore, one can again plot the present day energy density that is contained within the gravitational wave versus frequency, and one can tell that how large or how small this coupling can be depending on the choice of our free parameters. And here you see that I'm giving an instance here where the inflaton goes into a pair of scalars, and you see that couplings as small as 10 to the minus 18 is is completely ruled out because it is forbidden by the Planck measurement on delta effect. So again, the same primordial gravitational wave, which is helping us to constrain or put some bound on the nature of the coupling between the inflaton and the pair of visible sector particles. One can further go a bit more. One can do a bit more. One can now ask the question that what if I produce a dark matter in such in such a scenario? By such a scenario, I mean where the inflaton has a time-dependent decay width to some visible sector particles. Here, for example, I choose the production of dark matter through some non-renormalizable operator, which typically looks like suppressed by some scale lambda UV. And here, the production happens through what we know as the UV precision of dark matter. And remember that the inflaton always decays into visible sector particle, and the dark matter production happens through this kind of an interaction, which is suppressed by this new physics scale lambda UV. Then, depending on the choice of this new physics scale together with the dark matter candidate, and what sort of channel for this inflaton decay you choose, then depending on which you can produce dark matter starting from, let's say, an MeV to at least as large as 10 to the 15 GeV or so. So this is also a way to show that how a time-dependent inflaton decay can influence dark matter production in a scenario where the dark matter is produced by some UV physics. And just a comment that depending on the choice of this exponent by which the scale factor changes, one can also show the dark matter production can be boosted depending on how large or how small this X is to be taken. Of course, that will control your background cosmology as well, as you can see over here. Now, since we're talking about decays, let's go a bit far. So far we have only talked about two body decays of the inflaton, where an inflaton goes into a pair of standard model particles. But if you introduce this gravitational interaction, then you cannot also forbid decay in which the inflaton goes to a pair of standard model particles together with the radiative production of a graviton, either from the initial or from the final state. And these gravitons can be energetic enough because they are producing from the decay of a very heavy inflaton, and they can also constitute what is known as of course, the gravitational wave. And their source is again primordial because they're getting produced during reheating from the decay of the inflaton itself. Now, in this case, typically the gravitational wave is a very high frequency gravitational wave, courtesy to the fact that getting produced from the decay of a very heavy inflaton. And in the high frequency regime, which really do not have much of an experiment that can probe this kind of a scenario. But of course, there are certain experiments which can do the job. But nevertheless, this is also a source of the production of gravitational wave, which is not discussed to a great extent. So this is how it looks like. So in the low frequency, the U decigo is perhaps the best sensitive experiment so far. So it still cannot reach. But at the high frequency, there's only one experiment which can do the job, which is the resonant cavity. Of course, I'm not going to the details of how this thing works. But of course, just to give you the idea that a high frequency gravitational wave is also possible to comprehend through the decay of an inflaton. Now, since we were talking about gravitational, reheating or gravitational production of standard model particles in the very beginning, here we first told that, well, gravitational production is the production in which a pair of particles getting produced through the S-channel mediation of graviton. But that's one way, of course, to put this thing. But one can also imagine a non-minimal coupling between the gravity and the inflaton, like this, which has a coupling strength of xi. Now, once one go from, let's say, the Einstein, from the Jordan to the Einstein frame and make all the interactions diagonal, of course this phi will eventually decay into all the standard model particles, which meaning that it can read the universe. Here we are choosing a phi squared potential, which is typically ruled out from CMP data because it produces too large of a scalar to tensor ratio, so that it cannot it cannot explain the inflation in a proper way, keeping within the data. But thanks to this non-minimal coupling, now we can tune this accordingly, and one can see that even with the phi square potential, the universe can undergo inflation, maintaining all the observed bound on ns and r. But on top of that, also this inflaton can decay to all the standard model particles such that the reheating happens before the ppn. And what is important over here is the fact that in this case, if one only considers reheating from the decay of a non-minimally coupled inflaton, of course, single inflaton, then all of this depends on only one free parameter, which is non-minimal coupling xi. And xi can decide what the mass of this inflaton can be, how large the maximum temperature can be, or how large the reheating temperature can be, which is very fascinating because everything is determined by only one free parameter over here. Now one can again do the same trick as before and introduce more exotic particles, more exotic features, and say that, well, what if I introduce a singlet scalar on top of the standard model particles, or singlet fermions on top of standard model particles? Then of course this singlet scalar or the singlet fermions even can play the role of a good dark matter candidate. And in case of a singlet fermion, they can undergo again the semi-violating decay and can produce the observed matter-antimatter asymmetry. And here I'll show you the parameter space. You see this branching because everything is now happening through the decay of this inflaton. So the inflaton has a branching to the standard model, to the visible sector, which is maximal because you have to reheat it, and there's a very tiny branching to the invisible sector, to dark matter or to the dietary neutrinos. Then depending on this branching and the masses, one can again produce the right amount of relic density, or can explain the matter-antimatter asymmetry through the decay of this dietary neutrinos over here. So what we are trying to say here is that with a simple phi squared potential, which is quadratic potential, of course, one can again explain the inflation. One can reheat the universe, and not only that, one can also explain the matter-antimatter asymmetry and the dark matter energy budget once we introduce more exotic stuff along with the standard model. So this is basically an example where one can resurrect the quadratic potential with the help of a linear non-minimal coupling. So this is typical. This is at least what I had to really say. So I will try to summarize whatever I was telling so far. So as I was telling from the very beginning, that standard model does not include gravity, of course, but the occurrence of gravitational interactions are inevitable because thanks to its the nature of having this Planck suppressed coupling to everything. So gravitational interactions are something one needs to take care of. And then only taking the gravitational interaction is not enough. One has to also build simple particle physics models, and they can play a role together. They can conspire among themselves and can provide the standard model bath, which is of course the reheating. They can explain the dark matter abundance depending upon what sort of new physics particle you are adding with the standard model. They can also explain the Baryon asymmetry. Again, you have to have some source of semi-violation, for example, phi leptogenesis. And the goodness of these models is that they have very few free parameters. You don't have to deal with like thousands of couplings and masses. You don't have to tune them. And sometimes they can only have one parameter, as I was giving an example just before here. For example, everything is controlled by a single free parameter. And that's something we always want, not to introduce more free parameters. They also can have some observational aspect in the front of gravitational wave, because primordial gravitational wave can be produced during inflation, and depending upon the fact that if during reheating there is a stiff epoch, which means the energy density of the inflaton decreases more faster than the radiation itself, then you have this two tilted part of the primordial gravitational wave spectrum that can be detected with the help of futuristic gravitational wave. Not only that, these gravitational waves are typically in the low frequency regime. In the high frequency regime, you can also have something like a Bremsstrahlung process, where an inflaton decays into a two-body final state along with the radiation of a graviton, and this graviton can constitute the gravitational wave that can perhaps be detected with the help of more sophisticated experiments. So finally, let me discuss some outlooks. So far I have been emphasizing on the word perturbative, because I was cunningly trying to avoid more intricate scenarios, which is known as preheating, because preheating precedes reheating, during which you can have a burst of particle production, exponential particle production, where this perturbative scenario perturbative approximation is no more valid, and one needs to invoke the lattice simulation. This is something I guess it's a very dynamic field right now, and people are doing many research in this direction. There are many packages available, for example, cosmolattice and etc. And this preheating can also be a source of gravitational wave, and that is something perhaps one needs to study in a greater detail. And there always remains a window to explore more in the connection between particle physics and cosmology together with gravity, because there are many experiments in both front, and one should try to have a complementarity between all these searches, so that they can put some firm ground or some constraint on the new physics scenarios. And of course, beyond freezing, there are many dark matter production mechanisms. For example, SIMP, strongly interactive massive particle, co-SIMP, etc. And I guess there will be many in years to come. So this is something, again, one needs to think about, that how to break our bias towards WIMPs and go beyond the WIMP paradigm to search for more exotic dark matter production mechanism. And finally, since I have been talking about gravitational production, although gravitational production is not exactly in the truest sense of the term, because those who are really pedantic, they will be saying that, no, this is not gravitational production, because it did not take care of the fluctuation of the metric, you did not consider the Bogoliubov transformation production from the vacuum itself. Well, everything falls in a broader sense, gravitational production. So I must also mention the production from primordial black hole evaporation, which people have been doing for maybe last couple of years. And that's, of course, another story. This will take maybe another seminar altogether to discuss. So that's it from my side. Thank you very much for your attention. So I'll be happy to take questions.
Thank you very much, Basabendu. Very nice talk. Are there questions from the audience? Cannot see in the chat. Well, I can start. So just out of curiosity, so you have this data from colliders and laboratory experiments. What do you have in mind? I mean, is this in the context of gravitational dark matter or in general?
No, in general, not necessarily gravitational dark matter. So let me be more specific. For example, first order phase transition may be right. So it can be triggered by the presence of some new scalar, which gets a non-zero vacuum expectation value, and that scalar can always be searched at the collider. So that first order phase transition can provide you greater gravitational wave. So there is a complementarity between gravitational wave and collider searches in that sense. But perhaps it can also be extended to gravitational production of dark matter itself. But I don't know that how to do that. Perhaps that one can think about it.
Okay, thanks. Further questions? Okay, I have another one. So in the previous slide, or well, even at the very beginning, so we were talking about these low frequency blue tilde gravitational waves.
Yes.
So in the plot you show at the beginning, exactly there, for instance, next one, I think, okay, well, that one. You have this for alpha tractor or some particular model for
Yes.
inflation.
Yes.
I was
Yeah.
just wondering how model independent can this statement be? Of course, if you
That's
have a blue tilde spectrum, of course you have to be careful, but
I mean, that's a
ju-
great question. I mean, the requirement of having a blue tilt is that you need to produce, you need to have this like a stiffer period, right? So this equation of state that you have to maintain. So so you always need some sort of potential, which is typically, let's say, monomial in nature, right? Phi to the k. So in that sense, it I mean, well, alpha attractor is well motivated, but any phi to the k potential can do the job as long as you have this period where this steep up comes.
okay, yeah, I see. But okay, again, you say that this corresponds to alpha attractor, right?
This typically I am taking this alpha attractor potential, keeping this in mind.
I see.
Yes.
Okay. Good, thanks. Have maybe time for a last question. Joel.
I have a question for Basabendu. Yes. So I was wondering if you have any comments about regarding with the Hubble constant tension, in the sense that is any possible explanation between these kind of fields that affect the late time evolution of I mean, not the early universe, but just a bit later.
Yeah, yes, I get the point.
Yeah.
But honestly, I do not have any sort of idea regarding how to resolve this Hubble tension with the help of you have to control the Hubble rate, right? That how the Hubble rate changes, whether it's faster in the early universe and slower in the late universe, and so on and so on. But I have seen like many people trying to do it with the help of very how should I put it, like very intricate models, keeping many particles, keeping them together. But honestly, I do not know that how to resolve this issue with the help of this kind of feature, with the help of like a gravitational production or gravitational mediation. I really don't know.
Thank you.
Excellent. I don't see more questions, so last chance. So, okay, if not, let's thank Basabendu again. Thank you very much for
Thank you
this
so
very
much.
nice
Thank you
talk.
so much.
And let me just remind the audience that next week, Wednesday, we'll have another seminar by Rebecca Lane. So she will talk in just 1 hour earlier than usual. So next week, Wednesday. So thank you very much and hope to see you next week. See you guys.
Ciao, ciao.